So this is a collisions question we're just going to do, and the problem is we've got a snooker ball here that hits a cushion at an angle, like so. So we're told that the initial velocity of the cue ball is 20 meters per second, and it's along the horizontal, and the angle of the cue, or the cushion here, is at the inverse tan of 4/3. Now, to do this problem, you want to be thinking about where the collision happens. So instead of having the angle like this here, it makes way more sense for us to visualize it rotated, so that the angle rotated all the way back to here. So now, instead of looking at like the cue ball coming across horizontally, the cue ball is hitting it at an angle and going off. Now, the reason why we're doing that is because that's how we had the velocity initially, but instead now we're rotating it so that the velocity is in that direction there. This angle here now, I'll just get a pen to put this in. This angle here is still the same as the angle that this rotated down. So we rotated this down an angle of tan to the -1 of 4/3. So this angle here, because that's rotated down, we're taking this velocity is also rotated down. That angle there would also be tan to the inverse of 4/3. Now, just to put a few extra lines in this. So now that we have the velocity, we know that the magnitude of this velocity is 20 meters per second, and we know that it is directed down like this. So we can break that down into our I and J component. There's our I, there's our J component. And then when this cue ball collides with this surface down here, the collision will only happen in the J component, and the I component here will stay the same over here as it moves away. So that is our problem now. I'll just put in maybe 2 extra lines just to show where the collision happens, and we're good to move on now. So I'll just fill in some of these numbers again on this, it just works easier for the sums. We have this here, we know the angle, that's our angle theta, and we know tan inverse of 4/3 is equal to theta. We know this magnitude here is 20 meters per second. So we'll just maybe fill out that right angle triangle quickly. Now, if I have a little right angle triangle that goes from, let's say, there, I'll just do it again. Go this, there we go, across and up like that, meant to be a right angle there. Maybe just throw that in there. This is the tan inverse, so the opposite is 4. If that's theta, the opposite would be 4, this would be 3. And this would be our hypotenuse, 3, 4, 5. So the square root of that squared plus that squared. So we know that cos theta is equal to the adjacent, 3/5, and sine theta is equal to 4/5. So whenever you get this kind of format of question, you always work out what this cos and sine is. So we know theta is here. Now, first one here, and I'll do it in blue. This here is the adjacent component of theta. We know the hypotenuse is 20, so this is going to be 20 cos theta. But we know cos theta is 3/5, so it's be 20 multiplied by 3/5. The y component, I'll do it in green here, is the opposite component, so it's going to be 20 hypotenuse multiplied by the sine of theta, which is 4/5. So that's the same as 20 times 3/5 is 60 divided by 5 is 15 meters per second I, and this one here is 4 fours are 16 meters per second J. So I might just write that now in this reference frame. So the velocity of our object, so before the collision, the velocity is equal to, we might call it, is equal to 15I, and and minus 16j. Maybe I should specify what we're asked to find here. So for this question, what we're looking to find is the speed of the ball after the impact. I might just make a bit of space up here at the top and just list the stuff that we're looking for now that the question is set up. So we are looking for the speed of the ball after the impact, and we're also looking for the magnitude of the impulse due to the impact. Impulse due to the impact, and loss in kinetic energy, and I'll leave it at that for these questions here. Just number them. So those are the three things we want to work out from this problem. So there's another little bit of information that we had, that the coefficient for restitution, was equal to 3/4. So that will come into the J component. Now, we already know that after the collision, so that's before, after the collision, the velocity will still have the same I component. It will still be 15I, but it'll be plus something J. And the letter we'll give that, we'll just call it plus C times J. That's before and that's after. Now, there's a couple of things we need to know, so we might just go with Newton's law of restitution. Okay, so just to continue now, there is a small mistake here I must correct first off, and that is that 20 times 3 divided by 5 is not 15. 20 by 3 is 60, divided by 5 is 12, so I better correct that there. I better correct it down here as well, so that's the I component is 12I. And the I component over here should be read 12 as well, so I'll just do that in the correct colour. So just skipped a line, that's where I made a mistake. So 12 meters per second I, 12 plus, okay, so we're good to go now. Now we need to work out the speed of the ball after the impact. Now we already know the I component, because the I component doesn't change through impact. It just goes, it stays the same. It's going to be 12 meters per second for the whole way, because the whole impact happens in the J direction here. So it's the J component that will be changed by, it's the J component that will be affected by this coefficient of restitution. Now to work out the next part, you really want to consult with your log tables. Now the log tables are here, we can see them, so this is page 51 of the log tables. And what we have here is, it tells you a few different things. We have the momentum, mass times velocity, Newton's experimental law, which has the coefficient of restitution, which is what we're interested in, is here. And the wording of this is very important. This sign is crucial. So for two bodies, V1 and U1, U stands for the initial velocity of body 1, 2 stands for the initial velocity of body 2. So if there's only one body, you can just have V is equal to minus E over times U. We've got the conservation momentum as well, which can be used, but we're going to be using this problem, we're using the impulse, which is I is equal to the integral of forces with respect to time. What we're going to do actually is we're going to use it in this form, which is mass times final velocity minus the mass times initial velocity. Now we can move on, then we can go back to the problem. So those are the equations we're going to be using here. I've got them already typed up here. So with this one, I just multiplied both sides, or divided both sides by U1, U2, and it's the exact same as the form that was in the log tables. Now the way we're going to use this is slightly different, so I'll just maybe just amend that. So it's going to be minus E is equal to V over U, final velocity over initial velocity. Now we know the initial velocity in the J direction. I'm just going to highlight them in this blue highlighter here. It's this one here, 16 meters per second. Minus 16, so that's going to go into the initial there. We know that C, it's given to us in the question, coefficient for restitution is 3 over 4. It's going to go there. And then what C works out to be will come from this number here. And we have to be very careful of signs here. So I'm just going to put in, first off, the minus sign, minus 3 over 4 is equal to U, or V, which is going to be C is what we've used in our problem. And that's minus 16. Now that's really important to include the sign of the J component there, and with our coordinate system, that is definitely negative. So when we get C is equal to, multiply both sides by minus 16, we get minus 16 times minus 3 over 4. I'm going to go the long way around because I make less mistakes when I do it this way. So it's 16 times 3 over 4. 4 divides to that once, 4 divides to that 4 times. So the final velocity here works out to be 12 meters per second. So I know that after, so I can write that again, the velocity is going to be 12I plus 12J. Now that's the velocity. If we were asked to find the speed, so the speed we're given as the magnitude of this velocity, so it's going to put it as, that's V is equal to that. So the magnitude of V is equal to, you can draw out the right angle triangle for the two vectors, but it's going to be 12 squared plus 12 squared, which is the square root of 12 squared plus 12 squared, should be 144, which works out to be, if you put that in your calculators, 12 root 2. 144 plus 144 is 288. You can factorise the 2 out, and then that's where that comes from. So the speed is 12 root 2 meters per second. Now we just go back up to the question. That's part 1 done. Part 2 is the magnitude of the impulse due to the impact. So impulse, we're going to use this form of the equation, and we got it from our log table, so I'll do it in different colours so it's clear. So mv minus mu, so the magnitude of the impulse. So we know that what we're interested in here is, we've got our mass, which I didn't actually state at the start of the question, which I will now, and we left it as a mass m. We're just going to call it as a mass m. So we have n times the final velocity, which is 12I plus 12j. 12j minus n times the initial velocity, which was 12I plus or minus 16j. Multiply these out, and we get 12 mi plus 12 mj, m times 12j, minus 12 mi plus 16 mj, minus by minus there. So what you'll notice here is you've got that one there and that one there can cancel, and we get 12 plus 16, which is equal, so the impulse is equal to 12 plus 16, which is 28 mj. That's the impulse, the magnitude of the impulse. Oh, that's the side, that's the impulse imparted. Just go back to the question just to make sure if it said the magnitude then. So this is a word to watch out for. Magnitude means that there's no vector involved. Now because it's only along one direction, the magnitude of I is just simply equal to 28 m. You would lose a mark there if you didn't notice that it asked for magnitude. Final part is the loss in kinetic energy. So part 3. Now to get the loss in kinetic energy, you need to use the formula for kinetic energy, which is in the log tables as well. It's kinetic energy is equal to 1/2 mv squared. So the kinetic energy before the collision and the kinetic energy after the collision, and you subtract them. Now the important thing here, actually this should possibly be written as the kinetic energy 1/2 m. I'm just going to change the wording of this. It's actually the magnitude of v squared, because energy is not a vector quantity like all the others. Energy doesn't have a direction associated with it. So we know the magnitude of u, the velocity before the collision, was equal to the magnitude of it. We got it, we worked it. It's the length of this vector here, which is 20 meters per second. Now we could have just squared that, and got the square root of it using Pythagoras' theorem, but we know it's 20 meters per second. We know the magnitude of velocity after the collision was 2√12 meters per second. So, change in kinetic energy, the delta is sometimes used for change in kinetic energy, is equal to the final kinetic energy. 12/2 it is, yeah, thanks, sorry, small mistake there. It should be 12, let's get it there, 12 times √2. So the change in kinetic energy is the final kinetic energy minus the initial kinetic energy. So I'll just put I there, I'll just put an F, so final kinetic energy and initial kinetic energy, and I'll just sub these in. So we know it's 1/2 mv squared 12√2 squared minus 1/2 m times 20 squared. So we have here is, I'll just leave the colours as they are now, it's 1/2 m, this squared is 288 minus 1/2 m, 20 squared is 400, which is equal to 144 m minus 200 m, which should be equal to minus 56 m joules. And that's the final answer for that section. So I'll just zoom out of this so we can look at the whole problem in its entirety there. And we see that what we've worked out was, the first part of this problem was rotating the system. We found the speed of the ball after the impact, we found the magnitude of the impulse due to the impact, and we found the loss in kinetic energy. So that's the full question out.